Full disclosure before we get started. I am an astrophysicist. I've been an astrophysicist for a long time. In fact, I am a cosmologist. I have personally studied the structure, age, history, evolution of the universe. And what I'm going to present to you on this discussion on the crisis in cosmology is my own personal viewpoint of the subject. And this, I'm not alone in this viewpoint, but then there are other cosmologists out there who would disagree with some of the things I'm about to say. The contentious parts are at the end. I'm just going to build it up at first, which everyone will agree on. So I thought that would be best if I just get my biases out there. I do have a biased perspective on this. I do have a particular take on it as an expert in the field. Other experts in the field have different takes on it, but I thought it would be better than me trying to pretend to be objective. So I'm just going to give you my thoughts. And we need to start off, what is the fundamental question here? The fundamental question when it comes to this crisis in cosmology is that we are trying to measure the age of the universe. We are trying to measure the current expansion rate of the universe. We are just trying to measure the overall history of the universe. This very, very basic kind of numbers. Just how old is the universe? How fast is it expanding right now? You'll find the crisis in cosmology put in a few different ways. Sometimes some news articles might say, astronomers disagree about the age of the universe, or some of them might say, astronomers disagree about the Hubble constant. It's basically all the same. It's just different ways of looking at the same thing. The Hubble constant, by the way, I do need to get this little bit of jargon out. The Hubble constant is not really a constant. It's the rate of expansion of the universe today. Like right now, how quickly is our universe expanding? This number has changed with time. This number was smaller in the past. This number has been bigger in the past. Like it just changes with time. How we get this and how we translate the expansion rate today into an age of the universe is through modeling, through equations, through math, through science. This is how science works. Science is a mathematical model of the universe. And so, here we are trying to describe the whole entire universe. What we use to model the universe is general relativity, Einstein's equations of gravity. Einstein's equation of gravity, general relativity relate the stuff in a system to how the system evolves. So now we're applying it to the universe. We're going to take what the universe is made of and translate that into how the universe evolves, translate that into an expansion rate. We do this through what are called the Friedmann equations, which are a particular solution to general relativity as applied to the whole entire universe. Friedmann equations are pretty straightforward. You plug in what you know. We got this much normal matter. We got this much radiation. We got this much dark matter. We got this much dark energy. You know how these components evolve with time, and then you can use that. You can crunch through the math, and you can get an expansion rate at any point in time. Once you know the expansion history of the universe, you know the age of the universe. That's it. It's actually a pretty straightforward equation. It's not very complicated. Doing the actual measurements and observations is a little bit of the complicated part. So our goal to measure the age of the universe, we have a few different approaches. One of the approaches is through what's called the cosmic microwave background. The cosmic microwave background is the leftover light from when our universe was just 380,000 years old. It was super hot and dense. It was a plasma early on. As the universe expanded, it cooled off. The first atoms formed, and that released a bunch of light. The light has hung around for a few billion years, like a dozen billion years, and then we can detect that light. And so we get a literal picture of the universe as it was billions and billions of years ago. From this picture, we get an immensely accurate portrait of what the universe was made of back then. We know how much dark matter, we know how much radiation, we know how much normal matter was around back then. How do we know? Well, the physics of the universe when it was 380,000 years old, it was just a hot plasma. It was like the surface of the sun. Like, we actually understand that physics relatively well, or very well. And so we can use that, our understanding of physics, compare it to this picture, figure out what the universe is made of. I could do a whole separate series of videos on the CMB, or cosmic microwave background, which I have. I'm not just waxing, I was a member of the Planck collaboration, which was the satellite mission that the latest all sky maps of the cosmic microwave background. I was a part of that team years ago. So the CMB is very near and dear to my heart. It's an exquisite observation. And from those observations, we get an accurate portrait of the contents of the universe. We plug that into the Friedman equations, and then you can follow it up to the present day. You can calculate an age of the universe. You can calculate the expansion rate, the Hubble constant as it is today. You can do all that stuff because you have all the ingredients for the recipe. The CMB, however, does miss one ingredient, and that is dark energy. Dark energy was not present, or wasn't a major player when our universe was only 380,000 years old. Dark energy only really came online about 5 billion years ago. And so we can take our CMB observations, and then we add in the dark energy part, and then we're able to get the expansion rate as it is today. We're able to predict that value, estimate that value based on all those measurements taken when the universe was only 380,000 years old. The advantage of that approach is that the data that you get from the cosmic microwave background, it's like so wonderfully good, super high quality. The math is pretty straightforward. The modeling, the physics is pretty well understood. So you just get this exquisite data set. There's another approach to measuring the history of the universe, the expansion rate of the universe today, which is to measure the expansion rate of the history as it is today. You can just directly measure. You can skip the model and just go right for the measurement. And the primary mechanism is through supernovae, especially a particular kind of supernova called type 1a. Type 1a supernova, this is what happens when you have a binary star and material from one star falls onto a white dwarf and it reaches a critical threshold and it goes kaplooey. And because it's pretty much the same physical setup every time one of these things goes off, they have the same intrinsic brightness, like the same absolute level of brightness, or nearly absolute, or you can do some massaging of the data to figure out the brightness. So what you do is you spot one of these supernovae in a distant galaxy, you measure the distance to the galaxy, and then you measure by using the supernova, and then you can also measure how quickly the galaxy is receding away from you. You do this for a bunch of galaxies all over the place at a bunch of different distances, and you can build up nearby the expansion rate as it is today. Again, it's a pretty straightforward method, at least to say. The physics of supernova are a little bit messier than the physics of the cosmic microwave background, but you do get to skip all the modeling stuff because you're just directly observing the expansion rate. This can only take you back so far, because you can only see supernova so far away. Eventually they become too far away and too dim for you to observe, and so it gives you a very, very local picture. But this is how we discovered dark energy in the first place. Back in the late 1990s, we were using supernova and we discovered that the expansion rate of the universe is accelerating, hence dark energy. So it's obviously a useful technique. Here's the crisis. When you take the cosmic microwave background, get an accurate measure of the contents of the universe, plug it into the Friedman equation, add in dark energy, then you get the expansion rate as it is today, and you get a number. And then you go out with supernova, and you measure that number, and the numbers are a little bit off. The Hubble constant, the expansion rate of the universe today, from these two different sets of experiments are a little bit off. Not by much. We're talking like 10 million years. The universe is 13.77 billion years old, and the measurements are off by like 10 million years, which is amazing. So it's not like we're like, the universe is 50 years old and 1,000 years. No, these like very, very close, but it's precise enough our uncertainties in each of these measurements are small enough that these differences are significant, are meaningful. You can't just say, oh, well, it's just measurement uncertainty, who cares? These appear to be real discrepancies. Okay, so you might be wondering, why should we trust at all this measurement taken when the universe, from light, when the universe was 380,000 years old, over 13 billion years ago, plugging into a model and then predicting what the expansion rate is today? Why should we trust that over the actual measurement of the expansion rate today? Why should we believe anything other than the direct measurement? Here's the thing. The supernova, the use of supernova, isn't as clean as that. For one thing, we don't have a lot of supernova. You know, at most we have like 100 or so. We have like a few dozen reliable supernova. So right there, you don't have a lot of data points. The cosmic microwave background has tons of data points because you're taking all this information from the entire sky and correlating it together. It's just soaking in information. Supernova are a little bit more sparse. Second, like I said before, the physics of supernova are a lot messier and more complicated than the physics of the cosmic microwave background. The cosmic microwave background, it's just a plasma, and like we got plasmas. But stars blowing up, like those are some of the most complicated physical systems in the universe. It takes a lot of work. It takes a lot of massaging in order to turn stars blowing up into a measurement of the expansion rate of the universe. It's not a clean, clear-cut thing. It's good enough that we're able to measure dark energy. It was good enough that people were able to use it to see dark energy. We even gave away some Nobel Prizes for it. Like, I'm not saying it's unreliable. I'm saying it's very, very, very messy. In order to make this claim about the expansion rate of the universe using supernova, you have to really understand supernova. Like, really. Because if there's something in the supernova data that you don't understand, it can mess up your final result. And that your statement about the expansion history of the universe can be off, can be wrong, if you misunderstand something about how supernova work. So we have this crisis, where cosmic microwave background results plugging into models are giving us one answer for the expansion rate, and then supernova are giving us a slightly different answer. One possibility is that the cosmic microwave background data are junk. Like we messed up the observations, we misunderstand the physics. Basically, no one says that, and I'm not just saying that because I was a part of the Planck collaboration, but we worked really hard. There were like hundreds of people on this collaboration. We constant cross-checks. The data has been out for like half a decade now. It's been cross-checked and validated by independent groups. Like, there are no ghosts in the day. We really, really do understand the cosmic microwave background data. It's relatively unassailable. Like, no one really is saying like, well, maybe the observations were junk. Maybe you screwed it up. No one's really saying that. So that seems like a no-go. Another option is maybe we don't understand dark energy. Remember, in order to get the present day expansion rate of the universe, we need to plug in dark energy. And maybe we're missing something about dark energy. Maybe it's more complicated than we thought. Maybe it changes with time. Maybe it like interacts with dark matter in a weird way, like all sorts of things. Like, okay, you can twiddle with dark energy to make this crisis go away. You basically make the Friedman equation more complicated by adding some more ingredients in, and then you can agree with the supernova results. Another answer is that maybe the supernova results are a little wrong. The whole crisis rests on 6 galaxies. There are half a dozen galaxies with supernova observations that are critical for getting the uncertainties down to a certain point, for getting the measurement to a certain position where this crisis exists. 6 galaxies. it could be that our measurements, that our understanding of supernova are a little bit off. And it doesn't even have to be like wrong. They can just be more complex than we are assuming. And so the uncertainties in that measurement are a little bit larger than what we think they are. And once the uncertainties are a little bit larger, then the crisis goes away. Because it just turns out like, yeah, supernova are messier than we thought, and we're not as precise with this measurement as we thought we were. Sorry about that. We're actually a little bit more uncertain than we thought we were, and so the crisis goes away. I'm personally, and this is my opinion, like I personally believe Adam Rees, he won a Nobel Prize for discovering dark energy. I kind of believe that like if the only reason the crisis in cosmology exists is because Adam Rees wants it to exist. He discovered dark energy. He uses supernova. He's been using supernova for decades. He's the one making the claims about this. He's the one that says we understand supernova to such a high level of precision that this crisis exists. And so something has to give. Either the Planck CMB measurements are wrong or our understanding of dark energy is wrong, but our understanding of supernova is not wrong. That's what he says. Honestly, if Adam Rees didn't care or moved on to other projects, probably this crisis would just go away. Because the easiest place, I'm not saying the correct place, but the easiest place to resolve the crisis is for supernova to be messier than we thought. And considering that this is literally stars blowing up, that's not such a crazy thing to say. If supernova cosmologists were willing to admit or discovered that their uncertainties are a little bit larger, that they don't understand supernova as well as they thought, this whole crisis would go away. I understand why they're not doing that, because they honestly believe that they do understand supernova to that high level of precision, that they do understand that they do have control of the messiness, that they can make this claim of very, very small error bars, and so the crisis persists. Okay, fine. But when you look at the range of papers of potential solutions to the crisis, there are papers that say, okay, maybe we need to modify dark energy, which, okay, we don't know anything about dark energy. Sure, like feel free to play around with it. But then there are also papers that point out like, hey, if stars are like rotating faster than we thought, or have a range of rotations and the range is bigger than we thought, then the crisis goes away. Like, to me, that seems like the simpler solution. That maybe supernova are messier than we thought, but maybe dark energy is messier than we thought. The CMB is not messier than we thought, sorry. I don't know. This is my perspective. I don't personally think the crisis in cosmology is that big of a crisis. I'm guessing that in 5 to 10 years, it's just going to go away. I don't think it's going to lead to new physics. Astronomers, cosmologists are super interested in it, because if it is true, this points to a potential new understanding of dark energy, which we desperately need. We've been studying dark energy for 20 years and we've got nothing. We don't have any better understanding of what it is than we did 20 years ago when we first found out about it. So we, in a sense, cosmologists want the crisis to be true, because then it means we have something to play with and something to study dark energy. But if it goes away, then it's just back to like, yeah, we don't know what dark energy is, so we're done. So in a sense, cosmologists want it to be there. It's an excuse to print a lot of papers and talk a lot and hold conferences. There's entire conferences about the crisis in cosmology. Unfortunately, I just have this mantra. If it's interesting, it's probably wrong. More complicated dark energy is super interesting. To me, that's probably wrong. The more boring solution, which is supernova are messier than we thought, is to me the more likely one. That said, you're going to see headlines for it for years. Eventually, I think it's just going to go away. But that's just my take. Take it or leave it. Thank you so much for watching. Please go to patreon.com/PMSutter so that I can keep studying the cosmic microwave background. No, so I can keep sharing science with you. Like, share, subscribe, do all the stuff, and I will see you next time.